Not maybe. Okay, let's look at the practice problems. So here we have a second order ODE. And the notation with the dots means the derivative with respect to time. So this is second order derivative, and then this is the first order derivative. So to rewrite it into a system of first order ODEs, the first step is to write it in the standard form. And this is already in the standard form. So x double prime is equal to minus k divided by m, x minus c divided by m of x prime. The second thing is to define auxiliary variables. So make W0, define it as x, and define W1 as the first derivative. And the third step is to take the derivative of the auxiliary variable. W0 prime is equal to x prime, and x prime is already defined as W1. And W1 prime is x prime's derivative, so x double prime. Then what is x double prime? We look at the standard form. So x double prime is minus k divided by m of x minus c divided by m x prime. And when we want to rewrite x and x prime with respect to w, so we already define x as w0, and then we define x prime as w1. So then we can rewrite this as w0 prime is equal to w1, and w1 prime is equal to minus k divided by m, w0 minus c divided by m, w1. And the question also asks to rewrite the ODE system in terms of x and v. So when we are defining here, this is x is position, and x prime we know from calculus, this is velocity, or v. So to rewrite this, we have substitute everything about W0 as x. So we have x prime is equal to substitute W1 as v. So x prime is v, which is expected. The first derivative of x is velocity. And then the velocity's derivative is equal to minus k divided by m. W0, we substitute x, minus c divided by m. W1, we substitute v. So this is our final system of first order ODEs. Any questions? So this follows the algorithm from in lab 5. And yeah.
How we would code this, like specifically, how do we code it?
In Python.
Yeah.
Yes, that's practice problem 2. Yeah. Okay, any question on this part? I think this is also demonstrated in Monday's lecture. Okay, now practice problem 2. So we have some initial conditions, and we want to find the solution of x and v for different constants in some time. So let's define all the parameters we have. So first we define initial conditions. So x of 0 is 3 meters, and then v0 is 1 meters per second. So these form the initial conditions. And we have constants, physical constants, as m is equal to 3, k is equal to 3, and c is equal to 1. And then we have time. So time, t minimum is 0, t maximum is 30, dt is given as 0.1. So we can form a list of t. So because we know the step size, we use NP arrange from t minimum to t maximum with a step size of dt. But because we want to include the t maximum, we want to add a dt here. We can confirm it by printing it. Let me run NumPy. Okay. So we confirm that it starts at 0, ends at 30. Okay, so we define the constants, initial conditions, and the time. Now we want to define the ODE systems. So the ODE system should be a lambda function. It should always be a function, not a list. And it depends on the independent variable t and the list of dependent variable z. So z is a list. And then it contains the list, contains two things. Contains the dx dt and dv dt. So dx dt and some argument, and then dv dt, some argument. So we want to define these. And we also want to define these as lambda functions and never lists. And then what are they dependent on? They're dependent on x and v for both of these. So let's make them dependent on x and v. And then dx dt from the first equation, dx dt is equal to v. So in Python, we just say dx dt lambda function is v. And similarly, for the second line, dv dt is minus k divided by m times x minus c divided by m times v. So I'll write that down. Minus k divided by m times x minus c divided by m times. So we defined dx dt and dv dt. Now we need to look at their argument. So because these do not depend on t, we just leave it here. We just don't use it. SciPy always require you to put it here, but you don't necessarily have to use it here. And z is a list of the dependent variables in the order of 0th order derivative and first order derivative. So we can just expand the parameters as using this unpacking syntax star of z. So this is equivalent to if I type z of 0 and z of 1. It's the same thing. So this unpacking syntax means that I'll unpack this in order. And so now we have defined the ODE system. So constants, initial conditions, time, and ODE system. Now we want to solve the ODE system. So we can use SciPy integrate solve by VP. And the first argument it takes is the ODE system. The second argument it takes will be the bounds of the T. So we can define a variable called T bounds as T of 0 and then T of -1. So this is recommended because it avoids floating point error. If you define it as instead, if you define it as T minimum and T maximum, it might cause a floating point error because when it's arranging, it might not arrive at the same exact 30. It might be 30.00001. So I would recommend using this form to avoid floating point errors. Okay, so the second argument is the T boundaries. The third argument are the initial conditions. So we can also have an initial conditions list as x0 and b0. So that's the third argument. The fourth argument is T eval, and we put that as the T that we defined. So we run this, we see the result is successful, and what we care is all about y. So if we do dot y, there's the array. And then we look at its shape, it's 2 by 301. The shape of the time is 301. So it means that there are 2 rows to this array. Each row represents x and v. And then there are 301 columns. Each column represents a time point. Okay, so we will store the results. So this dictionary as the ODE solution. Okay, and you can verify this ODE solution is an dictionary. If you want the result, you should do dot y. So retrieving the y component. Okay, so these are the array. If you want to plot this, so I think it wants to plot this in a 2x1 grid. To do that, we have big X is equal to plt.subplots. 2x1, so 2 rows and 1 column. Okay, like this. Axes. So the axis 0, the 0th axis, we want to plot the time. And on the y-axis, we want to plot x of t. So we have ODE solution.y, the first or the 0th index. So this is the x solution. And similarly, on the first or index, we want to plot the v velocity. So ODE solution.y, retrieving the first index. So that gives us the velocity. And we can do some adjustment to look at their colors. Make one blue and then make one orange. And then we can also label them. So set y label as the first one is x of t. And the second one is v of t. And on the x-axis, we have t. So for I in range, because this is common setting for the two graphs, I can use a for loop. So axis dot I set x label as t. So this will appear on both graphs. And then PLT dot tight layout so that they are not crammed against each other. So you can see the labels now, t. And then we might also want to add a horizontal line. So XH line at 0. So we know where are they going to. So color, black, line style, dashed, and then line width 1. So we see that the position oscillates and eventually dies down to 0. And the velocity also oscillates and dies down to 0. And we can set the x limit, so the time limit as t of 0 and then t minus 1. Axis of I set limit. And then we can also set the y limit. So let's say this is minus 5 to 5. Okay. So we can verify that indeed the x starts at initial condition of 3 and v starts at initial condition of 1, and they oscillates because it damps down with a damping constant of 1, eventually dies down to 0. So it stops moving, so velocity is 0, and then the position is also at the equilibrium position 0. Okay, any questions on this problem? So we basically recreated in lab 5, how do we reduce a second order ODE into a system? Then we use scipy.solve IVP to solve the system. Okay, and to expand on this system, we can look at its phase portrait. A phase portrait is a visual representation of a dynamical system, and a dynamical system is some system that depends on time. And the x-axis and the y-axis will represent some parameter of the system. And you can plot the trajectories or the lines within the system, and you can see how it evolves over time. And you can also plot the slope field. That's a grid of arrows that indicates the derivative of the systems. And let's demonstrate that with the system that we already just solved. Okay, so in this axis, we want to plot the parameters of the system. And the parameter of the system are x, the position, and the v, velocity. So we want to plot it in the x coordinate and the y coordinate. So ODEs solution dot y of 0, so this is the position x. We plot it on the x-axis. And then on the y-axis, we'll plot the first index, which is v. So this is what we got as a phase portrait. So let's label the axis. X label is x of t, and then the y label is v of t. And we note that this is not entirely accurate because the aspect ratio is not 1, and the distance between these are also not equal. So we can set the aspect ratio as 1. Okay, so now the spacing should be same. And we can also set the box aspect to 1 so that it becomes a square. Let's also plot horizontal lines on 0 and vertical lines of 0. And then set the colors, line style, and line width. Okay. And I also set the x limit from minus 5 to 5, and then y limit as the same, maybe larger. And then we have this trajectory, but we don't know where's the starting point and where's the ending point. So we can plot the starting point. So this is the trajectory. And then now we want to plot the initial condition. The initial condition we can get from this trajectory as the 0th index. So if we look at the x component, if we index another 0, this will give us the first element. If we index -1, this gives us the last element. So we can do that by adding the 0 index and then make it a dot and then assign it the color. So here is our starting point. And similarly, we can also visualize the final point. So we copy this, and instead of using 0, we change this to -1, so the last index. And then let's make it a cross with color red. So it starts here with position of 3, velocity of 1, and the system evolves so that it goes to 0 position, equilibrium position, and 0 velocity at rest. Okay, so this we plotted the trajectory, initial condition, and the final condition. And we can also plot the slope field. So the slope field represents in a grid where the system will go. So to demonstrate that, the slope field, say we have a figure, so we have a x and y. A slope field is, first you have a grid of points. So all those points should form a grid. And now all these points will give you an arrow, and these arrow will indicate the derivative of the system. So if we look at one single arrow here, its x component will give us dx dt, and its y component will give us dy dt. And then this is the length. Okay, so how do we represent this in Python? So in Python, there is a command called, so we want to plot the slope field, called quiver. Quiver basically is an arrow. So if you search on Google, this is the first one, x.quiver. So it's a 2D field of arrows, and you can look at some examples here. So these are the arrows. And how do we implement that? We want to look at the call signature. So it has x and y, which defines the arrow locations. So if we have some arrow here, we want its x position and then the y position, represented in big X and then big Y. And then U and V defines the arrow direction. So this is U and then this is V. And then C is an optional color, and the color should be proportional to the length. And to implement these, let's try a simple quiver. So let's say we want to plot the slope at 1, 1. So the x position is 1, and then y position is 1. And then we'll plot some derivative. Let's say the derivative is also 1 in both directions. So here is the arrow. So it's located at 1, 1. So let's make it 2, 2. So 2, 3. So we'll distinguish them. So x is 2, y is 3. And then the derivative on the x component is 1. The y component is also 1. So it's 45 degrees. And we want to do this for all of the points that we want to specify. So in this problem, we specified we want 20 by 20 arrows. So we're given the number of arrows in some range. Since we're already given the number of arrows, we can use NP linspace instead of NP arrange. So we want to define some x vector as NP linspace from -5 to 5 with 20 arrows. And similarly, we want a v vector as NP linspace -5 to 5. We have 20 arrows. Okay. And what are these defining? If we look at these are 20 points along the axis. So we defined here 20 points in x vector, and we define here 20 points in v vector. But we want to have 20 by 20 points, so 400 points inside the grid. And to do that, there is a command in NumPy called np.meshGrid. And it takes in the x vector and the v vector. If you run it, what it returns are two things, two arrays. And each array, let's look at the first array, 0, and then look at its shape. Its shape becomes 20 by 20. So the first argument gives the x coordinate of all the points that it generates. And then the second argument gives all the y coordinates. So we can assign this as big X and then big Y as a matrix. And you can verify that they should also have the same X. And then if we want to apply to quiver, we want to feed in the position X and then Y as the XY coordinate of the quiver. And then the derivative, we already defined dx dt and dv dt. So we can call dx dt of x comma v. So let's make this v instead of y. It's more representative. And then dv dt of x and v. So here we plotted all the arrows. But you see that some arrows are small and small arrows are big because they have different length. So the scale are different. This is one way to represent this. The other way to represent this is to represent it by color. So we define a scale that is the length of the parameter. And the length, we already know that the length should be equal to the square root of dx dt squared plus dy dt squared. So let's define scale as np square root of dx dt squared plus dy dt, dv dt squared. And then we can normalize the length by the scale and then give it a color parameter scale. So now all the length are the same, but the length are being represented by colors. And you can also use the parameter that I introduced here. Scale is 25 and width is given. So we plot these. And this makes the arrows more clear. And you can also set the color map as C map is equal to, let's say, make it reverse winter. So these represents the colors. So the initial point starts at position 3, velocity 1, and it oscillates and then goes by the slope field as directed by the slope field and spirals down into 0, 0. And the phase portrait tells us that when there is a damping constant, it will usually go to 0. Any questions? Okay, so now with this knowledge, let's try the practice problem, this two-eyed monster system. And here the initial conditions are the grid of 15 by 15 points. So let's try that out. Let's come back in 15 minutes. Interesting. Let's print this in the Now, I think at some point you assigned np.arrange as this. So what we need to do is to restart, import it again. Hopefully it will solve the problem. Okay, restart the kernel. Okay, that's good. The reason is because I think you assigned np arrange as something. So if you assign this as a 0, then it can be a function now. If you do this, this will be a variable.
I didn't do that. Well, I thought. I don't know where that comes from.
So let's restart this because I also redefined it. Let's see. Yeah, this works now because that was solved. So ODE system.y. So because you already defined .y here, you don't need a .y here.
Oh,
so either way is fine. So you can remove this. It should give you the right answer. Oh, because the space here.
Oh. So why does it do it like this?
You look at the index.
Oh, there should be one. And so will it be published? Because I couldn't like do anything else because I was trying to fix this.
Yeah, so the guy, so this, I don't know why there is one. This is not a problem. So the guy, the problem here, this is basically the answer.
Okay.
Yeah, these
So
are
the next question.
to this question and this question, kind of.
Okay.
Yeah, so you only need to use this to solve this problem.
Okay, thank you for that.
I'll give some hints to this practice problem because the initial conditions might be a little hard to formulate. So here we have 15 by 15 points. Already know the number, so use length space. So x vector is equal to NP length space from -5 to 3, and then 15 points. And similarly, we have y vector from -3 to 2 with 15 points. And you can verify this on the vectors, 15 points. So we want a grid of initial conditions. Then we need NP mesh grid. And taking in x vector and then the y vector. And then we can assign the names as big X and then big Y. And you can verify the shape should be 15 by 15. Like this. So we have a grid of points. So if we want to plot it, we can say PLT dot plot X and Y. I hope this works. Oh, it doesn't work, I guess. Yeah, so these are the points. So you have generated a list of initial points. But how can we do it so that it can be used in the for loop? Currently, it can't be used in the for loop. So if you want to put it in a for loop, you want to make it in so that the columns are X and Y. And these are the points, 0.1, 0.2, 0.3, etc. So this should be a number of points. So this is 15 by 15 times 15, which I guess, I don't know, 225 times 2. So this should be 225 times 2 matrix. And how do we convert that from a 15 by 15 matrix of 2? So we do that. So if we have X, there's a command called reshape. And if we put reshape as -1, it gives you the shape of a vector. So now it's 225 times 1. And we can do the same thing for Y. So reshape it so that it's first dimension. So now we get the vector of X and then vector of Y. Now we can make them together with NP array. Remember the syntax for NP array? We have a list here. We get X reshape -1 and then Y reshape -1. And if you look at the shape, this is 2 times 225. But we want 225 by 2. So we can just do a transpose. So dot T is transpose. So now we have initial conditions, X, Y, and then the rows are the points. We can do this as initial conditions. Okay. So that's the hint. Try the other parts.
And if it's a woman, I'm a woman of the Lord, that's why.
It's already.
The sector itself is 1 by right up to the point. And then it's 50 by 81.
Oh. So it's actually the best one.
And also, one of the thing for
I just think this one from this one,
so the next one, adding 2.
Yeah.
That's the shop. 55.
Yes.
But what we want is, because we're writing for the one for each, we have one metric which is, and that two can be in society.
Right. Sorry.
So what we want to do is especially in the class, we have like, that's also an understanding to make sure it's going to be. So this line, two matrices, that has 2 unified points. That then together and one.
Well, this is really thick.
We shape the sense. We're not using change the shape. So it's not. And then I mean, it's the number
Those 5. This is 5 is that.
it's right now, foods, and then for example, you can also put it 6. I don't think 10 is the limit. So you should get you can from that. So you can do 9 by 25. So the minus 1 so it's replace this one. So it's 1
Right. Yes.
So
It doesn't do right.
giving back.
Okay.
Okay. All right. Thank you.
Okay, let's code this problem up. So we already have the initial conditions. And then we want to define the time. So T minimum is 0, T maximum is 100. And then because we are not given a step size and it doesn't really matter, so we can do linspace from T minimum to T maximum with 1,000 points. What else do we need? the ODE system, of course. So we define the system. So we have ODE system as a lambda function of the independent variable t and a dependent variable list of z. So the first one is dx dt, and the second one is dy dt. And let's individually define those. Dx dt is a lambda function. And then dy dt is also a lambda function. And they both depend on x and y, but not really t. So we have x, y. So dx dt is y plus y squared. Dy dt is minus 0.5 times x plus 0.2 times y minus x times y plus 1.2 times y squared. So in the ODE system, we want to unpack this z. So we have unpacking syntax z. And this defines our ODE. So we want to plot the slope field. To plot the slope field, we will need the quiver. So quiver, we first have x position, y position, then dx dt evaluated at x, y. And then dy dt evaluated at x, y. So these are the slope field if we don't normalize by their length. If we want to normalize by their length, we have scale is equal to the square root of the x component square plus the y component square. And we can normalize by the scales. This is what it looks. And then we can color them by scale. And then I think here are the scale and width parameters that we can set. Now I'll also change the color map to winter reverse. So this is the slope field. Any question? It's basically using the quiver command. Then plot the trajectory of the system for all the initial conditions using a for loop. So for I an initial condition in initial conditions, let's first print the initial conditions to make sure we have the correct ones. Okay, so the initial conditions are, wait. Okay, a list. Okay, so within this for loop, we want to solve the ODE. So SciPy integrate solve IVP. And then we input the ODE system, the T boundaries, and then we should define the T boundary as T of 0 and then T of -1. And then we want to define the initial condition, which is different within for each loop. And then T eval is equal to T. And we store this in the ODE solution dictionary. I think the initial condition is a little bit off. So for I in the length of the initial condition, let's also do a range. Oh. Second. So what I'm doing here is that I'm making the initial conditions. First, I get the length of the initial condition, and then I generate it with a range. So if you make this a list, it goes from 0 to 225. So it will iterate through our initial conditions. And here we're using the ith initial condition. And so I have solved the ODE, but I haven't plotted it. So let's plot the result. So on the x-axis, set x label, we have x. And then on the y-axis, we have y. So on the x-axis, we plot the 0th element. And on the y-axis, we plot the first element. And then let's make it points that are dots, black dots. These should be trajectories. It will take a while to compute. And now our next, oh, whoa, okay. Oh gosh. So first I made the points. Instead, I should make it a line instead. And the second thing is that I want to constrain everything to the initial position. I'm not interested in what goes on in the other x and y. So I should set the x limit to -5 and 3. Where is it? And then I'll also set the y limit to -3 and 2. Okay, so let's run it again. So these are the trajectories starting at every point. So let's also plot the initial conditions. So what are the initial points? The initial points is the 0th element of the list. And let's now plot it as points. And also let's do final conditions. That is the -1 index. Let's make it cross with color red. So here, each dot represents the initial condition which we generated as a grid. And then the red points here, the red crosses indicates the current or the final position of the points. So you see that the points that have the initial condition that's near this loop, or we call this is one eye and then two eyes, around this eye loops around and then got all sucked in at this point. And then the other points circles around this region, but never goes in. And we will rigorously define these in future lectures, but we'll just now enjoy this as a beautiful graph. Any questions? So in this problem, we plotted with quiver the slope field, and we also plotted the trajectory, initial and final points with a grid of initial conditions. Okay. The second problem I want to look at is that in engineering applications, we usually have a system and we have many different physical parameters that we can tune. And we can tune them and simulate them to see what are the effect of the physical parameter on the system. And in this case, we consider the same spring mass damper system as in practice problem 1 and 2, with the same initial conditions and constants, except that the damping constant C, we have 3 values. So we want to plot the phase portrait of the system and how they evolve in time. So all the code are the same. I'll just copy and paste all of above, except that I modify the C as a list of 3 damping constants. Okay. And now I want to plot first the phase portrait. So the phase portrait should be a 1x3 grid because we have 3 C's. So let's make it 1x3 and then make it a fixed size of 15 inches by 50 by 5. And then in that axis 1, I want to plot something. So I want to plot the solution of the phase portrait. So I want to solve the ODE, but I have different C's. So what I should do is to use a for loop. So for I in range, the length of C, I want to solve the solution and then plot the trajectories. To solve the ODE, again, it's scipy dot integrate dot solve IVP. Solve IVP. Okay, and it takes in the ODE system. But here, the ODE system that we need to redefine. So let's go back to problem 1. So here we define the ODE system. But what's different here is that we have a different C. So here C is defined as a list. So we need to change this C as C of I so that it indexes the list correctly. And then the other things are the same. So T boundaries, initial condition, initial values, and then the T eval as T. And then let's store it as ODE solution. Okay, let's run this. And then let's plot the trajectory. So axis of 0, the axis of I. So because here I'm iterating with the list. So let's plot the solution y of 0, which is the x position, and then index 1, which is the velocity. And these are the trajectories. Let's make it nicer by setting the aspect ratio as 1 and the box aspect also 1. And here we don't know where the initial and final conditions are. So let's plot those two. So plot the initial condition. So we'll just index the list, the 0th element of the list. And then similarly, we can plot the final conditions. And instead of using 0, we use -1. Then we can change. So the initial condition, we make it a dot. The final condition, we make it a cross. And then make the color red. So this shows that when C, so this is C is equal to 0, let's label that axis of I, set title as a format string of C is equal to C. And then label the X and Y axes, set X label as X of T, and set Y label as V of T. And the limits are not the same, so we can't really compare them. So let's also set their limits. So set X limit as -4 to 4, and then set Y limit as the same. Okay, so now they're comparable. So C, it should be C of I. So when the C is equal to 0, there's no damping. So it just oscillates and oscillates. But when C is positive, we see that it slowly decays because it's being damped down, but it's not decaying that fast. But when C equals to 1, the damping is really fast and it goes down to 0, 0. So now we plotted the trajectory, initial condition, and final condition. And in part B, we want to plot the phase portrait for each of those. So within the for loop, we also want to do a quiver. So axes of 1 of I, quiver. So we want to use the X and V. So we have X, V, and then dx dt evaluate at X and V, dv dt evaluate at X and V. And again, we can use the scaling factor, calculating the distance. So the X component square plus the Y component square. Normalize them by the scale and then make the scale the color. And then also use the parameters given, which is scale of 20 and the width. You can make the color map or the C map, whatever you want. you can look in the documentation to what they offer. I think they also offer spring and summer and winter, so you can change that. Okay. So this shows us that initially it's at here, so it follows the slope field and goes around, and then here as well. But the slope field changes subtly that in the no damping case, it constantly oscillates, but with the damping case, it oscillates down to 0. And for C is 0.1, it takes longer time to oscillate to 0. Any questions? Okay, with this example, now you should be able to, okay, there's the other part that plots the trajectory, which is exactly the same as what I did before, so I won't demonstrate that. But with these examples, you can now complete practice problem 4 and 5, which lets you to look at different masses and different spring constants. I'll be here until 1:50. I have midterm to do it. So I'll be home and speak. Right, so because first we want to constrain it to the original. That's the first question. And then let's try to so where it goes.
We go with this problem, solve it for 2 days. We don't tell what we have. Where we are. So come in now, which time doesn't work. Kids are saying, you want to lose it. I was like, I don't know if that's what that was. We. I don't know. I don't think it says on the. But it's usually. And I think it should be more.
Does it?
I mean, it doesn't even. Who? It's like a yes. Somehow, the NP is going to slowly see, like, that's involving.
So I guess it's because some of the T values, this is what's supposed to. Is there any part of the or?
What's just.
Steps.
That makes sense. There's no meaning. This was just like. Oh, it's fine.
Let's look at the.
So. What's he done is just two.
Okay, that's just.
Yes, one still. No, this is 2022. Yeah. I'm sure you guys maybe should. It's okay. I can write it otherwise. We also just play it.
So you start. Final.
It's probably not bad. Well, also, there's so many things. So you can. We're also. I don't like the CEO or something. Just show. We need a fun. Like, you're not one. I don't want to get.
No, I can't.
At this we don't have the slides anymore, so there's
The right trajectories.
Oh, the GT makes sense. You're putting the whole.
you write it.
He says it was. The boards is ignoring. Because this I have unsure.
Sorry.
Sense. You said if you're is it 3 or 4? You need someone.
Oh.
Should it not be in Oh. What can those do to
Close it.
So.
He doesn't have to tell me what to do. That's not being That's what it sounded.
So that's just like, it's coming, you know, more of the shape. That's
But why?
Yeah. Yeah. Okay, so. It's 2 by
What if we do with chocolate and we get that Uber guy to come and give us chocolate and you also supplement with Yeah. You don't have some.
No, I can't.
Did you eat the chocolate that's
You are solving a, ODEs. Right, but. So variables. So that is two. So.
Yeah.
The first midterm, I think it's right. Oh, no, she's not going to be or something. What is that?
How about we email them? We all. I thought you have to, they made a thing where you have to. Eco loss. There's a famous person. Is it printing? It's a very good.
No, this is not a fault.
You got it.
Oh, shoot.
I got it. Okay. Did you go on the one? I don't know. Why is it boring?
It won't be so much.
Huh?
Oh, not.
Oh, maybe you could. Have they be alive?
It's
How do we email like Pepsi?
watch that.
Or like, can you send something to help? Do you have a? You should put your experience. Like, can you send a case of Pepsi and like a presentation from the?
Let's see.
Actually, we're so ugly now.
So.
Oh, this.
Everybody we have free house of lecture. We can also. So, fortunately, that is offered.
And
Don't do that part.
Maybe it's good, it's very like time steps.
It's very much, they started with some basically with some of the
Right now it's 14.
Okay, so.
I know I'm not trying.
Getting my place.
Well, this one here.
Taking engine 7 weeks.
Yeah.
So it's a problem of this has that abilities. So your, this is your foundation. It's
And
Yeah.
you really.
Can I just put like on?
Importance.
That's like the first step.
Because I want to do the basics. Actually, no.
It's just here's one. But we should never.
This is
So, oh, 100. Is it printed?
Look at the lecture. And also encourage you to call me from that.
Probably usually comment
Just look at the.
your option plus this one.
Yeah.
Maybe it's counter errors and also solving errors. Check something with how to
Like one.
Polygon.
I'm sorry, it's not. Sorry.
not me, but the GSA and the instructor.
Oh, it's-
we have almost every day. It's always a.
So.
Okay, yeah, I mean, the office hours for the line.
Yes.
It's
Oh, for the line. Me specifically, it's one, but you can also. Other GSA.
Yeah, it's the
It's not.
Can we try and print it?
No, we haven't.
then like, for so for example. 40%. That's what.
Not sure. So that's my estimation. Like if you look at the, it's like 2016, 20, it's like 16, 56.
Oh, 6.
So I think interesting. So there's no all of myself. So the problem is, if it was the original it has 106.
I didn't put this, maybe I need to put these.
Yeah.
Because I need that, it's between my fantasy.
I think you can just send your, so when you're so. I just said for me. Yeah.
Are they innovating stuff?
Now see the.
I looked up, and I was like, do you sponsor events? But here it goes all the way to the voice. I don't think it should go all the way to break.
See. That's now that we're going.
This is, we can find that option. Maybe I should just like put the names. It's got lots of cows. Ow. We're gonna go to those cows.
Yeah. Because,